if I am drawing this, maybe complete one look like this. Right. This is how it looks like in 3D. If you are looking from top, if I am looking from top, this look like this one. Right. These two are n plus, and this is top is my gate. This is made up of polysilicon. Right. This is how the top view look like, and this is how the elevated view look like, or the front view, whichever view you will say, right? So this is generally known as the layout, right? So this side is known as width, this side is known as length. Actual one we call it L, and this one we call it W, right? Here also, if you want, we can call this one as L, and just overlap area, this is the width. Okay. So this is how the transistor look like, having gate, sorry, drain source, any one of them, whichever you want to consider. This is source drain, and this one is gate. And body is, where is the body, by the way? In this particular layout which I have drawn in the top view, the white part on the board, white part, entire white part is substrate, entire white part, okay, it's the substrate, right? So this is generally known as the MOSFET. In this case, this is N MOSFET, right? Similarly, we can make the P MOSFET also. It's not a big thing. We'll talk about this maybe afterward. But now what is happening over here is, just remind me, I have to talk about FDSOI when I'll be in the frequency response. Otherwise, here it will be difficult to explain. Right? Just remind me when I'm teaching frequency response, I'll teach about FDSOI. Right now, it will be difficult. Okay. I'll keep it somewhere. FDSOI. Frequency response. At this chapter, I can talk about this. So any one of the technology you can choose, and I was saying about the digital one where this becomes 1 volt and this becomes 0. If you are going below, let's say 1 volt, it is very difficult to identify logic 1 and logic 0. It's very difficult. Why it is difficult? What do you think? Sorry?
Is a pre-decided at a fixed value?
No, pre-decided means who is going to decide? We have to decide. So I am saying I am going to have problem. If I am going like below 1 volt, digital logic 1 and 0 is difficult. Why difficult? Hmm? What do you mean by error? Hmm? Noise margin, yeah, that's the thing, right? So here the logic 0 and logic 1. The good part of digital is there is you can have always a margin for logic 0 and logic 1. So if this is logic 1, this is logic 0. Understand? In this particular region of voltage, so this is voltage with respect to time, but this is logic 1. If this is VDD, this is ground, so I can treat ground and nearby this area, I'm going to call that one is logic 0. In this area, I'm going to call it logic 1. There is always a noise margin high and noise margin low. this maybe you are going to study in a digital course, right? So always noise margin high and low are there. However, there is some gray area where it's undefined state, right? It's neither logic 0 nor logic 1. So as we are going down, this viridic is going down, it's getting very difficult to identify logic 1 and 0. And in that case, it might happen that you are going to have, or you are landing up in the analog only. There is no other choice. You can't make it everything with digital, or you have to do something at the analog level so that digital people can work it out properly. So that's the problem, and that is the reason why we are not going below actually 0.9 volt. That's the voltage available with the TSMC 28 nanometer. We are using 0.9 volt, right? One more thing just for information. There are some of the terminology we are going to use it. So this is a chip. Inside the chip, whatever I am keeping, it's known as the core. Okay. And outside this, there are something called IO pads, PON pads. True. Right. So these are the IO pads. IO for input and output pads are there. Right. And outside to this, black, so this is core, and then this is IO or IO pads. Then this side outside, there are actual pins are there. The chip, right? So these are the pins. It might be at all four sides also, right? And they are connected with this one with something called bonding wires. Right? And by the way, the whole thing, the black color, is known as the package. These are the just terminologies we are using sometimes in VLSI. It is irrespective of branch, analog, digital, or anything. People are using this, so these are the meaning of that. Right? So if you are using, please understand that. If you have any doubt, just let me know whenever there are some doubts. Okay. So what we are going to do in this course. So the course content goes as follows. So we are going to deal with small signals. We are not going to deal with large signals. We are going to deal with the small signal. That's why to understand MOS basics, we are going to make the small signal model. Right? So small signal models or model will be there for NMOS, PMOS, and using the whole thing, we are going to analyze how the circuit works, or we will find out the transfer function. We are going to find out different dynamics of that. So we are going to use following things. Understanding of signals and systems are very important thing. Then control theory, network theory, and basic things we have studied in undergraduate level, analog. Even though I am going to give you some of the bridge theory so that you can understand things, but these things are going to be there, which is going to deal with the whole course content, right? So these are kind of prerequisites, I would say. Okay, so then things will be easier. The course is not so much difficult, but what is the difference between this analog and this analog? First of all, the UG level analog also deals with BJT. As the name suggests, we are not teaching anywhere anything on BJT. However, some of the topics we may touch, right? And this analog has the laboratory component. So everything which we are studying over here, we are going to design it on computer, right? We are going to simulate it, right? So those are the things we are going to do with some of the technology. As I told you, all technologies are different. Their PDKs are different, right? PDK is, what is PDK? Process design kit, right? This is a very popular thing. Generally in company or industry, people are saying, okay, you have this PDK, or which PDK you are working in. Right? So these are the things people are asking each other. So right now, like most of the industry people are dealing with 3 nanometer PDK. So the current technology node is 3 nanometers for designer. However, for process engineers, it is one level down. So they are working on it. Once that is ready, then they are going to give us the technology. They have to find out whether those technologies are working or not. Right? So device engineers are one technology node ahead of us. Right? We are going to study the design of amplifier, and that is the whole goal of this course, that we want to make operational amplifier, the triangle. We want to design it completely from start to end on our own, from the scratch, right, using MOS transistors. So that is what our goal is, and we want to design that, but it requires lots of tips and tricks. Understand what I am speaking in class may not be working when you are going to design it on different PDKs. If you are designing with, let's say, 350 nanometer, it's very easy. It will work. Whatever I am saying, it will work. 180, the things are getting worse, and you will feel that at the level of 28 nanometer, you will not able to design anything, or you have to invent some technique to which it will work. So everyone will have different technique. I'll tell you my technique to design. So my tips, my tricks, which is not written in any book. So it is coming through the experience only. Even my TAs have designed it, or they are designing. So they will also tell you the exactly how to design it. Sometimes some tricks are there. Sometimes we are not going to tell you immediately. You have to work for 1 week, 2 week, and then we'll give you the answer. Right? So that is what we have to do, and the whole game is about achieving the specifications. The required specifications for different application will be different. If I am designing something for, let's say, mobile application which is of 5G, then I have to design my op-amp with the bandwidth of something like 5-6 gigahertz, right? So it's very large, or wideband amplifiers have to be designed. If it is for sensor application or biomedical, this whole thing goes to hertz, right? ECG, EEG, or other sensors might be like kilohertz, not going beyond kilohertz, right? So those specifications derivation is difficult job. It's not being done in India. Any of the country, I'm referring to the all big players. So people are designing here, like your manager will tell you that you have to design this op-amp with this specification. But the most difficult part is called op-amp architect design, who is going to tell you the specifications of entire system and block by block system. He is getting more salary than you, by the way. Okay. So once designer is designing this for almost for 20 years, then he goes to the next level, right? But we are going to study that also, that how to, I'm going to give you some of the application where you have to design just specifications. No design, like there is no requirement of op-amp designing or anything, but you have to just design the specifications, and what will be the requirement for that op-amp for going into particular sub block of any system. So those will also be part of this particular course. So that is what we are going to study, right? So if time permits, and I can teach you something called band gap reference. It depends on your interest and my pace, depending on your understanding. I'm not in hurry. I'm just going with your pace, right? So if you want to cover it, band gap reference, it's possible, but it requires another 6-7 lectures. Just op amp, when we are going to study the op amp after the all these amplifier frequency response, we require at least 13-14 lectures only on op amp, right? So out of 42 lectures, we require something like 13 lectures or 14 lectures on op amp design. So we'll spend some time on that, and then another band gap reference requires another 5 to 6 lectures. So if you can complete all these things around in 25 lectures, then this is possible, or less than 25 lectures. But it depends on your understanding, your previous understanding. So I don't know. So with the time, we'll go accordingly, right? So any other things you want to ask? Or if I forgot to add something, just let me know.
FDSOI.
FDSOI. FDSOI also has same symbol, by the way. As I told you, my tips and tricks will work for any transistor, including BJT. We don't study explicitly, BJT or LDMOS or FDSOI, but these are very easily, you can extend it to any transistor. There is no problem. If you want, you can take 28 nanometer FDSOI technology and design it. It's same thing. The equation changes. The IV equation and other things will change. At the back end, the circuit equation will be different in that PDK, right? That you will never experience, right? You will always see this one as a transistor. The dynamics are different. So when IBM and ST, these are the two people who have started the FDSOI. So they were advertising FDSOI. It's same transistor. The only difference between FDSOI and CMOS transistor is it's cooler, faster, and low power. So that's the actually only difference. There is no other difference than these three. Equation wise also look alike to each other. It's not much difference. Okay, so we are going to study following things. So this is again the whole course I am writing, right? So we are going to start sometimes, like it's also important that what is happening in neighboring course, which is digital, and it's very popular also. So how it's different, right? So we have to start with the large signal rather than going with the small signal, right? So we'll study what are the large signal, what are the small signal. Then there is something called parasitic understanding. You know what is parasitics? Hitesh, huh? What is parasitic?
For when we say resistor, but actually every resistor has some inductance and some capacitance. So whether we want it or not, some unwanted L and C comes into the picture whenever we design something. So that is parasitic. We adjust our design according to that.
Yeah. So if you are saying that this is a transistor, knowingly, unknowingly, there are some resistance, inductance, capacitances are there, and they are going to limit the performance, right? So maybe I can give you one example. So if there is a simple, line is there. This is, I'm applying here 1 gigahertz of signal. Other side, it is a wire, so it's going to see 1 gigahertz, right? Same signal. But if I'm going to keep it here, one parasitic, or let's keep different colored one, RC, whose combination is going to give you 1 kilohertz. By the way, you know that's 1 by 2 pi RC. So if these parasitics are going to have 1 kilohertz of frequency, what are you going to see here? Only signal with 1 kilohertz, right? 1 gigahertz won't go there, right? If you are applying just 1 gigahertz sine wave, let's say if this is a sine wave with 1 gigahertz frequency, then other side I am going to see nothing, 0, right? Because this is acting as a low pass filter, or it's limiting the whole thing, right? So that's why these parasitics are not visible. However, it's going to affect the overall performance in terms of giving you extra poles, zeros, and it will create lots of problems in terms of stability, right? You want to see the signal like this, but instead of that you will see that, okay, this is something like this, right? You might observe this when you are going to see exactly on oscilloscope, or when you are going to see that on our simulations also. But these are the effects because of those RLCs. So system goes under damping, over damping, right? So we have to tune it, or that particular tuning in control system, they call this one as compensation. So through compensation, we have to make that stable as per your requirement. So generally, for a given phase margin, we are designing it. So those things we are going to study in this course, and we are going to design an op-amp for a given, you know, given specifications. Some of the experimental understanding and everything, we are going to do it with the industry standard tool, which is Cadence. So we are going to simulate it. We are going to do it with the behavioral model, right? And not only these things, it's up to you. As I told, there are lots of analysis are there. You can see. So before going to that analysis, so what I did yesterday. Assignment was how much? 20%. Okay. Surprise quizzes 10%, right? This was 20, and this is another 20. Project PPT, project report, and lab report. Right? Something like this. Right? Okay. So if you all agree, then we'll go. Do you agree with this BTEX? Because if you look at this, I keep the whole thing, I mean, outside those exams. In these exams, you are not certain, but outside you are very certain. If you are regular, if you are doing all these things on time, there is no problem. Right? So as we have agreed, what's your name, by the way, the new BTEC guy? Abhishek. So Abhishek, we will have assignments exam. So 1 week before, I am going to give the assignment, and then during the class we will have the small examination, right? So same questions, no changing of data, nothing, same to same. By the way, yesterday I forgot to tell. So these both the exams will be open book. Okay. You can use any book, any solution. You have Bezaz solution, right? Please send it to everyone. Right? So we are going to use this book called this one, Bezaz Razavi. Most of my lectures will be covered from here. Right? Even though I am speaking from my experience, but most of the things available in this particular book. There are plenty of books available in the library, and those who wants to pursue analog as a career, I would recommend, please buy that. It will be very good for your career. Right? This is the only book used around the world for, even if you go to Stanford, you can go to any good place, all are studying Bezaz Razavi. Right? So this is blue colored book, by the way. There are two kinds of Bezaz Razavi is available. Red color is for undergraduate study. Blue color is for specifically for CMOS. Then there are many other colors are available for higher version of that. If you are going for mixed signal or PLL, SERDES, many things are there. RFIC design. He almost wrote something like 20 books. Okay, so use first 2 books. Right? Okay. So I was talking about simulations. So these are very important, that which simulation you are running. I believe you have done some simulations in your life, right? For circuit simulation. Have you done it, or so? With using what software have you used or made the simulation?
First ones will be
LT Spice, yeah, LT Spice. What about others? Ritika, Orchid. Okay. I haven't used Orchid for a longer time. I used it for PCB design long back, almost 20 years back. It can simulate, huh?
No, for PCB
Hmm?
only. PCB only.
Okay, PCB. Not the circuits. You haven't simulated any circuit.
Circuit also.
Okay. If you want to study how to use LT Spice, that video is also available on my YouTube channel. If you want to study that, right? So it's step by step how to use LT Spice. If you want to use, because everything was based on Spice actually. It has also full form. If you Google search it, you find the full form SPICE. It's abbreviated word, so it will be there. And later on, many version of Spice came. NG Spice, LT Spice, many Spice came, and almost like higher version of Spice came with something called BSIM. Have you heard about BSIM? So this is B stands for Berkeley. So there is one powerful group in Berkeley. So Berkeley simulator is the BSIM, and Berkeley simulator is actually designing PDK for all these, technologies. So they are using, so they are connected with Cadence people, and they are selling their PDKs to BCM. They are selling their BCM models to Cadence. So these are the BCM model which are running the Spectre. So Cadence and these two are connected to each other. Whereas Eldo model or by Mentor Graphics, so this is Spectre. These models are called Philips model. So they are designing for them, and these two are the only group who are working for these two companies. These companies came also from Berkeley and Stanford, and those people only they built these companies, right? And till date there are no competition. As I told you, you have to make some good model or simulation technique. Everything was based on, by the way, Spice. Spice is open source, whereas these are the paid ones. Okay, so BSIM has also many higher versions are there. We need to check which Spectre we are using. BSIM, which model? 6.5. So they are releasing different version every year. In industry, it might be something like 8.0 they are using, if I am not wrong. This is around 5 years old model which we are using. So as I told you, that's why Cadence is giving us their license at the cheaper rate, because they are not giving the full version. So we are having these, but still using this you can simulate it, and you can design your circuit. You can send it for fabrication, and you can you can have your own chip. By the way, just for your information, very few companies are there in the world who are actually designing or fabricating the chip. Do you know that? How many companies do you know? Fabrication company.
Samsung.
Okay, Samsung. Samsung. TSMC. ST Micro. AMS, that's Austria Microsystem. L Foundry for Italy. Anything else? IHP from Germany. Global Foundry. Taiwan has TSMC. Okay, TSMC is already. Tower Jazz. Tower Jazz is from Israel. And they are the one who are giving us the technology. We are calling SCL, but it's exactly Tower Jazz. their engineers are sitting there and they are not allowing us to see what they are doing. That is how this SCL works. SCL has 180 nanometers, so these tower jazz people has given to us, right? So it's exactly same tower jazz only. It's not SCL. We can say proudly, but it's not actual Indian company. And maybe which one? Intel, right? In Silicon Valley, there might be few, right? TI, Intel, all are same, right? They're combining like they are having like Qualcomm, all are getting same from same foundry, that is UMC, right? Or UMS. So they are getting from the Silicon Valley. So each one of the company has only one foundry. It's American fact, right? So only these many companies are there. Not many companies are there, right? So as I told you, the one license of Cadence costing in reality it's almost 1 crore. Then one chip we can't buy, right? If you are a company, you have to buy a wafer, right? Generally 6-inch and 8-inch wafers are there, right? 6-inch and 8-inch wafers are there, right? So if you are purchasing, let's say 6-inch, this value depends on the technology first of all. If it is 180 nanometer, it's very old, like 20-year-old technology, then this must be costing something like 2 to 3 crores. Right? If it is smaller technology node, I do not have numbers,